and welcome to today's class. And today we'll be looking at the simple theory of elastic bending. We'll be revising that. We'll be looking at how to calculate the second moment of area. We'll also be looking at tools such as the principle of superposition and the parallel access theorem. Okay, so let's think about simple theory of elastic bending. Let's consider a beam which in its undeformed state sits in this position. We then apply some moment, M, to our beam such that its deformed shape is going to look something like this. Now, what the simple theory of elastic bending shows us is that M over I equals sigma over Y equals E over R. Now, what are each of those terms? Well, M is my moment, so the moment which we're applying to the beam. So we're applying some M to this beam, moment to the beam. I is the second moment of area of the beam. So I describes the beam's resistance to bending. So if the beam has a high I value, it doesn't bend very much. Sigma is our direct stress. Okay, so if we consider a small section on the top of the beam, let's consider this piece of material here. It's being loaded in tension. Okay, we consider a small section on the bottom of the beam. It's being loaded in compression. If we consider what is known as the neutral axis, the bit which runs through the middle, that is in neither tension nor compression. Okay, so M is moment, I is second moment of area, sigma is stress, it's positive on top of the beam, it's negative on the bottom of the beam, it's zero on the neutral axis. It's a maximum on the outside surface, maximum tensile there, maximum compressive there. And actually what you can show is it's proportional to Y, the distance from this neutral axis. So what is Y in this term here? It is the distance from this neutral axis. So Y increases, the stress increases. E is our Young's modulus, the stiffness of the beam, stiffness of the material, and R is the radius of curvature. So what is the radius of curvature as I've drawn it here? Well, if we were to consider this beam here, the centre of curvature would be about there, and the radius of curvature is from that centre to the neutral axis. Okay, so that's R. So what can we show here? Well, if we ignore these terms here, what do we get? We end up with sigma over Y equals M over I. So therefore, sigma equals My over I. So what does that tell me? Well, as the moment increases, the stress is increasing. They're directly proportional. As Y is increasing, the stress is increasing. They're directly proportional. As I is increasing, the stress is decreasing. It's inversely proportional. If Y is 0, the stress is 0. Okay, so on the neutral axis, when y is 0, the stress is 0. Y is a maximum on the outside surface of the beam. That's where our stress is a maximum. If I increases, stress decreases. If m is 0, my stress must be 0. So all of those terms, m, I, sigma, y, e, and r. M is my moment, I is the stiffness of my beam section, sigma is my stress, y is the distance to the neutral axis, distance from the neutral axis, should I say. E is the Young's modulus, the stiffness of the material, and r is the radius of curvature. The only other thing you need to think about there, notice I've talked about stiffness there, the stiffness of the section and the stiffness of the material. And if you multiply those two terms together, E times by I, that is known as the flexural stiffness. It describes a beam's resistance to bending, and it has something to do with the material stiffness and the section stiffness. What is the material made? What is the beam made from? And what is the cross-sectional area of that beam? If you multiply those two things together, that is the flexural stiffness, EI. So clearly, if we're going to use the simple theory of elastic bending, we need to be able to calculate I for various sections, the second moment of area for various sections. So let's now have a look at that. Let's understand how we can calculate I for various sections. So definition of I equals the integral of y squared dA. So let's consider a section. We've got a section there, square section, rectangular section. Let's draw our neutral axis through the middle. This is d meters high, and that's the depth, and b meters across. It is the breadth. Okay, the origin is in the center here, so this must be this must be d over 2 at the top and minus d over 2 at the bottom. And we're going to work out the second moment of area of this section. We're going to integrate it. We're going to integrate all of these small sections. So let's call this small section here dA. dA is b meters wide, and that is y meters on the neutral axis, and it's dy meters high. Okay, so when we look at calculating the second moment of area, the integral of y squared dA is the same as the integral of y squared b dy. Okay, there we're integrating with respect to a. A is clearly a function of y, so we can, rather than writing dA, we can write b dy. So that's going to be b times by the integral of y squared dy. Okay, clearly b is not a function of y, so we can move it outside the integral sign. And my limits, let's put my limits in. B, we can be integrating between minus d over 2 and plus d over 2 y squared dy, which if we integrate y squared with respect to y, we end up with y cubed over 3, so that's b y cubed over 3, and my limits d over 2 and minus d over 2. We can move the 3 outside, the third, so that's going to be b over 3, lots of y. So let's put those as square brackets still. Y cubed d over 2 and minus d over 2. So if we were to put those limits in, what does that then give us? So b over 3, lots of d cubed over 8. So 2 cubed would be 8. So that's 8 on the bottom. So we've got d cubed over 8 minus d cubed over 8. So that's going to give me b over 3, lots of d cubed over 8 plus d cubed over 8. So I'm calculating is b over 3 times by 2d cubed over 8, which is 2b d cubed over 24, which is b d cubed over 12 higher. So if we're calculating the second moment of area of a rectangle around the neutral axis between d over 2 and minus d over 2, and it's b meters wide, I is bd cubed over 12. And we're going to use that. We're going to use that a lot. Okay, so remember that, bd cubed over 12. Now, notice with that example, the neutral axis ran through the center of the rectangle. We ended up with bd cubed over 12. We can show it in exactly the same way. If we have the same shape, if we have a rectangle, but this time the neutral axis runs along the edge of the rectangle. So this time, so it's not our neutral axis, we've got our axis along the edge here. So we're going to, our limits this time, instead of being between d over 2 and minus d over 2, it's going to be between 0 and d. Okay, so we're going to integrate our section. So this time we've got our section dA, and again it's y meters from that axis. Okay, so all we've changed are our limits. What we would end up with, what we can show, is that I equals b d cubed over 3. So when we're calculating the second moment of area of a rectangle around an axis on the edge of that rectangle, if that rectangle is b meters wide, breadth parallel to that axis, and depth perpendicular to that axis. Okay, but this time my axis is on the edge of the rectangle. We're going to end up with I equals bd cubed over 3. Okay, so we understand how we can calculate second moments of area of a rectangle if that axis for that rectangle runs through the center of that rectangle, and that is d meters high by b meters across. I equals b d cubed over 12, and if we've got a rectangle, the axis is on the edge of that rectangle, but again it's d meters high and b meters across. I equals b d cubed over 3. The other shape that's useful to remember for it is for a circle of diameter d. This time my neutral axis clearly runs through the center of that circle. So this is my neutral axis. And we can show that I equals pi d to the 4/64. Now that we've got those basic shapes, we've got a rectangle, we know how to calculate the second moment of area. If we've got an axis running through the center of that rectangle, we also know if we've got a rectangle and we've got an axis running along the edge of that rectangle, how to calculate the second moment of area. And if we've got a circle, we can calculate the second moment of area from an axis running through the center of that circle. We can calculate the second moment of area of an awful lot of sections using a couple of tools. The first thing that we can think about is the principle of superposition. So let's discuss that. Let's think about an I-beam. So we've got an I-beam which looks something like that. We can use the principle of superposition to calculate the second moment of area of that I-beam. If we calculate the second moment of area of this rectangle, the outside rectangle, around the neutral axis, and we know how to do that, it's BD cubed over 12. We can then subtract the second moment of area of this rectangle around its neutral axis, the red section, and then we can subtract the second moment of area of this rectangle around its neutral axis, the green section. What are we left with? We're left with the second moment of area of this shape, the bit in the middle. Okay, the bit that we're after, the shaded region. Okay, so the second moment of area of the big blue rectangle, I, the total I section for our I-beam, equals second moment of area of the blue section minus the second moment of area of the red section, so minus this bit, minus the second moment of area of the green section. So second moment of area of the blue section of the blue rectangle minus the second moment of area of the rectangle, red rectangle, minus the second moment of area of the green rectangle. So the second moment of area of the overall shape, the black shaded region here, is going to be equal to this outside dimension. Let's call this D, capital D, and it's B meters wide. So we can end up with BD cubed over 12 minus the red bit, and let's call this D by B. So minus BD cubed over 12, and then we're going to subtract the green section, which is also D meters high, B meters across. So that's going to be BD cubed over 12. So if we've got a section where we can calculate or create a shape which is the same as that section by calculating the second moment of area of rectangles around their neutral axis, we can simply use that, BD cubed over 12. Alternatively, we might have a section which is slightly more complicated, so we can't actually do that. Let's consider a T section. So let's consider we've got a beam which looks something like this. Okay, and the neutral axis of that beam is going to sit somewhere like that. Okay, so there's my neutral axis. Now, how can we calculate the segmental area of that section? Well, we can calculate the segmental of area of this first rectangle here around its edge. We know how to do that. So I for the total section, we've got this red region here around an axis on the edge of that axis, on the edge of that rectangle. And actually there's two of those. There's another one here, look. So that's going to be equal to two lots of red, equal to 2 times by segmental area of the rectangle, the red rectangle. We're then going to subtract this green rectangle here. You can subtract two of those actually. There's one here as well, look. So minus 2 lots of the green rectangle. And then we're going to add on to that this section here. And then finally, we're going to add on to that this section here, blue rectangle. Okay, so the green one, remember how we would calculate a rectangle around its edge is BD cubed over 3. So first of all, we consider the red rectangle there. We've got two of those. That's 2 times by BD cubed over 3. And then we're going to subtract. Now we're considering the green rectangle, 2 of those. This time B is the same actually, but D is different, look. So we can subtract 2BD cubed over 3. And then we're going to add this black rectangle. Yeah, so that's going to be BD cubed over 3. And then finally, we will add this blue rectangle here. Add BD cubed over 3. So this shape minus this shape, 2 of those, so that's going to give us this little bit here, and this little bit here, plus this black bit here, plus this blue bit here. However, sometimes we end up with a shape where we can't calculate the area, segmental area of that shape by using the principle of superposition. So we use something called the parallel access theorem. And all the parallel access theorem says is that I equals I around the neutral axis of that shape plus a h squared. Okay, so let's say we had a rectangle or some shape. Okay, and we wanted to calculate the segmental area of that shape around this axis. Okay, so my overall shape, some sort of compound shape, it's got this bit in here. Okay, so the overall shape, its neutral axis is there. Okay, so the segmental area of this rectangle is simply going to be the segmental area around its neutral axis, which is here. We know how to do that. That's BD cubed over 12. So let's say that is B meters wide, D meters tall. So I equals BD cubed over 12 plus AH squared, where A is my area. Okay, so that's the area of this shape. Okay, in this example, clearly that's B times by D. And H, the height, is this offset, this distance here. The height between the overall shape, the neutral axis, and the local shape, its neutral axis. Okay, so I, for the overall shape, is going to be BD cubed, the rectangle around its own neutral axis, the local region, plus AH squared, plus the area of the shape, this red section here, times by the height squared, where the height is the offset between the local neutral axis and the global neutral axis. So let's have a look at some examples using the simple theory of elastic bending. Example number 1. An I-section girder 200 millimeters wide by 300 millimeters deep with a flange and web thickness of 20 millimeters is used as a simply supported beam over a span of 7 meters. The girder carries a distributed load of 5 kilonewtons per meter and a concentrated load of 20 kilonewtons at the midspan. Calculate the second moment of area using conventional methods. Part B. Calculate the second moment of area using the parallel access theorem. Part C. Comment on the two methods used in parts A and B. Part D. Calculate the maximum stress that the beam will see. Part E. Comment on where the maximum stress will be and if it will be compressive or tensile. Okay, question 1. So we've got an I-section girder. So an I-section girder 200 mm wide. So there's my I-section girder. So the first thing that we'll do is draw a schematic of the situation. Okay, so we've got our I-section girder 200 millimeters wide. So this distance here, 200 millimeters. And it's 300 millimeters deep. So 300 millimeters deep with a flange and web thickness of 20 mil. So this is 20 millimeters. This is also 20 millimeters. This is a simply supported beam over a span of 7 meters. So that's my cross section. If I look at how this beam is being used, there's my I-beam. It is 7 meters long. Carries a distributed load of 5 kilonewtons per meter. So we've got a distributed load, uniformly distributed load of 5 kilonewtons per meter. And then in addition to that, we've got a 20 kilonewton load at the midspan. 20 kilonewtons. Let's call this RA, reaction A. Let's call this RB, reaction at B. Okay, and that load there is in the center. So that distance there is 3.5 meters. Okay, so the first thing we're asked to do is to calculate the second moment of area of the section using conventional methods. So using principle of superposition rather than the parallel access theorem. So we're going to use the principle of superposition to start with to calculate the second moment of area of this section. So the second moment of the area of that section is going to be equal to this section, the outside section, minus this section here times by two of those. Okay, and what we're going to end up with is the I-beam in the middle. Okay, so what have we got? We've got, we're going to consider b d cubed over 12, the outside shape, and we're going to subtract 2 lots of b d cubed over 12 of the inside shape. Now, the outside shape is 200 mm wide, so that's 200 times by 300. D cubed over 12. Now that's 200 mil, that's 300 mil, so that's 200 times 10 to the minus 3, 300 times 10 to the minus 3 cubed, so that's 300 times 10 to the minus 9 times 10 to the minus 12. So we can multiply that by 1 times 10 to the minus 12 to convert that from millimeters into meters. Okay, so that's the second moment of area of this large outside section. And then we're going to subtract 2 lots of the inside section. So if that's 200, it's 20 in the middle there. If we consider the halfway point, that bit there is going to be 10, 100 minus 10. So the section here, this rectangle is going to be 90 wide. Okay, so that's 90 times by my depth of my section. Well, this is 20 mil, this is 20 mil. This bit in the middle is going to be 300 minus 20, so that's 280 minus 20, so that's 260, so it's going to be 260. 260 cubed over 12, again, times 10 to the minus 12 to put that into meters, which is going to give me 4.5 times 10 to the minus 4 minus 2.64 times 10 to the minus 4, which is 1.86 times 10 to the minus 4 meters to the 4. So there we've used the principle of superposition to calculate the second moment of area of that rectangle by considering the second moment of area of the outside square and then subtracting 2 lots of the second moment of area of the inside squares. So part B says calculate the second moment of area of the same section, but this time rather than using the principle of superposition, we're going to use the parallel access theorem. So let's have a look at that. So let's calculate the second moment of area of that section. So we can consider this I-beam being made up of 3 rectangles. And there's my I-beam. That's can be considered to be this rectangle at the top, this rectangle in the middle, and this rectangle on the bottom. Okay, my global neutral axis for my shape runs through this point here, and we can see this rectangle at the top has a local neutral axis which is offset by some distance. And the bottom rectangle is also offset by some distance, and actually that's the same distance, h. And then we've got this rectangle in the middle, and actually the local neutral axis for that rectangle goes through the same axis as the global neutral axis for the shape. So we're going to have to shift the segment area of this rectangle and this rectangle, this bottom rectangle, the one in the middle, we're not going to need to change. Okay, so let's first of all consider this center web. Okay, so the web is the center section. We're going to consider that as BD cubed over 12. That is 20 mil thick, so 20. It is, the overall height is 260 minus 20, so that's 280 minus 20, that's 260 deep. So times by 260 cubed over 12. And then we're going to have to multiply that times 10 to the minus 12 to get that into meters. Is going to give me 2.929 times 10 to the minus 5 meters to the 4. So that's the second moment of area of that web. Let's now consider the second moment of area of one of the flanges. So this can be the top rectangle or the bottom. And that's BD cubed over 12. So we're calculating the second moment of area of either this rectangle or this rectangle around its local neutral axis. So around the axis which is running through the center of that rectangle. And that's equal to 200 B times by the depth, 20 BD cubed over 12 times 10 minus 12 to get that into meters. It's going to give me 1.33 times 10 to the minus 7 meters to the 4. Okay, now we're going to have to use the parallel access theorem. So using the parallel access theorem, for in one of the flanges. This time, so before we calculated it, segment vary around the flange local neutral axis. Now we can be calculating it for the segment area of the flange around the shape's global neutral axis. So we're going to have to offset it. So that's equal to I plus AH squared. So I, we've just calculated, so the segment area of the local shape around its local neutral axis, 1.33 times 10 to the minus 7, plus the area. One of these rectangles is 200 times by 20. And then, so that's the area and the height. So what are we offsetting? We're offsetting by, this is 300 mil. So halfway is going to be 150 minus that 10 now. Remember, this is 20. So 10 to the halfway point, so 150 minus 10, so that's 140 times by 140 squared. That's the height that we're offsetting. And again, we're going to have to convert that into meters. So times 1 times 10 to the minus 12. Times 10 to the minus 3 times 10 to the minus 3 times 10 to the minus 6. It's going to give me 1.33 times 10 to the minus 7 plus 7.84 times 10 to the minus 5, which is going to give me 7.853 times 10 to the minus 5 meters to the 4. So that's the second area of one of the flanges around the global neutral axis. Now that we've got those, we can calculate the overall shape segment of area and compare that to part A. And we're going to have to calculate one web and two flanges around the global neutral axis. So if we add this bit to two of these bits, we should get the same answer as in part A. So let's consider that. So total second moment of area equals two flanges around the global neutral axis plus web, which is 2 times by flange, which was this 7.853 times 10 to the minus 5. So that's 7.853 times 10 minus 5 plus my web. My web we calculated here 2.929 times 10 to the minus 5. So plus 2.929 times 10 to the minus 5. We add all of that, we're going to end up with 1.86 times 10 to the minus 4 meters to the 4. Okay, so in part A, we calculated the second moment of area of the section using the principle of superposition, and we got 1.86 times 10 to the minus 4 meters to the 4. In part B, we have calculated the second moment of area using the parallel axis theorem by considering the fact that we've got one web in the middle here, and the neutral axis of that web coincides with the global neutral axis. And then we've got two flanges, and we've calculated this second moment of area of the flanges locally around this section, around this axis, this section around this axis. And then we've had to offset them using the parallel axis theorem by some distance to get to align the local neutral axis with the global neutral axis. So we've done that. We've added them together, the two flanges and the web, and we've got the same answer, 1.86 times 10 to the minus 4. Part C then says, comment on when the two methods used in part A and B. And that's what I've just done. You know, you can see the answer is exactly the same. In this instance, actually, there's not a great deal of difference whether you use this principle of superposition or the parallel axis theorem, whatever you're more comfortable with. There will be some instances where one method is easier than the other method. But as you can see in that question there, both methods are valid and both methods will give you the same answer. Okay, So part D now says calculate the maximum stress that the beam will see. And here we will use the simple theory of elastic bending. Okay, and in particular, we will use two terms in that relationship. So what have we seen in today's class? Let's look at part C now. Sorry, part B. We're told from the simple theory of elastic bending, m over I equals sigma over y equals E over R. So we're going to ignore those two terms there and just consider m over I equals sigma over y. So therefore, m over I equals sigma over y. And we're asked to calculate the stress in the beam, calculate maximum stress. So therefore, we're going to rearrange that. So sigma equals my over I. Okay, we've just calculated I in part A and B actually. Y is our distance where we're calculating the stress, and the maximum stress is when Y is the maximum. So that's going to be on the outside surface of the beam. What we haven't got is M. We need to calculate what M is. What is the moment on the beam? So let's consider our beam. We've got our beam 7 meters long. 7 meters. We've got a reaction at this end. Let's call this RA. We've got a reaction at this end. We'll call this RB. We've got our 20 kilonewton load sat in the middle, such that this distance here is 3.5 meters. And on top of that, we've got our uniformly distributed load of 5 kilonewtons per meter. Okay, so the first thing we're going to have to do is to calculate M. Now, in order to do that, we're going to start at this end of the beam. We're going to go to where we're going to calculate the stress. Now, the maximum stress is going to be in the middle of the beam when M is a maximum in the moment is a maximum in the middle of the beam. So we need to calculate M in the center of the beam. Okay, so we're going to start at the left-hand end. We're going to go to the center of the beam. We're going to look left and we're going to write down our moments. Okay, so if I draw the center of the beam there, XX, what have we got? We've got RA. And we've got a portion of our UDL, 5 kilonewtons per meter. And we're going to write down our moment at position XX. Okay. Now, in order to do that, we're going to need RA. Okay, so we're going to go to this position XX. We're going to look left. We're going to need to know what RA is. Now, in order to get RA, let's consider this first situation. We know this is in static equilibrium. So therefore, we know two things. The vertical forces are equal and opposite. So the upwards force is equal to the downwards forces. And we also know it's not rotating, so therefore the clockwise moments are equal to the anti-clockwise moments. So we could say the sum of my forces equals 0. We can also say the sum of my moments equals 0. Both of those things must be true. This is sat in static equilibrium. So let's consider this first relationship. The sum of my forces equals 0, and more specifically the sum of my vertical forces. So the sum of the forces in the upwards direction equal the sum of the forces in the downwards direction. Now, the upwards forces are RA plus RB. And actually, if this is all symmetrical and equally loaded, RA and RB would be the same, wouldn't they? They'd be equal and opposite. Oh, sorry, they'd be equal in magnitude. Now, some of the forces acting down, well, we've got my 20 kilonewton load plus my uniformly distributed load, which is 5 kilonewtons per meter over 7 meters. So that is plus 5 times by 7. Okay, so that's 20 plus 35 equals 55 kilonewtons. Okay, now if RA and RB are the same, each of those is going to be half of that. So therefore, RA equals 27.5 kilonewtons, and actually RB would be the same, 27.5 kilonewtons. So let's now consider my moment. Okay, so we're going to start here. We're going to go to position XX. We're going to look left. We're going to write down my moments. Okay, so my moments equal my, I've got this section here, RA, and so that's my force. How far away is this force from this location here? Well, if we're in the midpoint of the beam, this must be 3.5 meters. So that's RA times by 3.5. Those are my clockwise moments. Okay, there's nothing else trying to rotate my beam clockwise around this position. Then we're going to subtract my anti-clockwise moments. So my anti-clockwise moments, so minus, so my moment which is trying to rotate my beam clockwise is positive. My moment which is trying to rotate my beam anti-clockwise, so around position XX, we've got this portion of the UDL. So it's negative because it's trying to rotate my beam anti-clockwise around this position. Okay, and that is the magnitude of the force is 5 kilonewtons per meter. So that's 5,000 kilonewtons times by the distance that it's acting over. So it's 3.5 times by, where do we assume it acts? We assume that this is going to be acting in the center. So if this distance here is 3.5, this distance here is going to be 3.5 over 2. Okay, so times by, so that's the magnitude of my force, times by the position, the distance to that force, 3.5 over 2. RA we've already said was 2,7,500 times by 3.5 minus 5,000 times by 3.5 times by 3.5 over 2, which gives me my moment in the center of the beam of 6,562.5 Newton meters. Now that we've got that, we know the moment. We've calculated I in the previous part, A and B, so therefore we can calculate Y, or sorry, we know Y, the distance to the top of the beam or the bottom of the beam, actually, for the distance from the neutral axis, which is going to be a maximum at the top of the beam and the bottom of the beam. So therefore, sigma equals my over I equals 6,562.5 times by, now this beam is 300 millimeters in cross section. If we look at the cross section here, the neutral axis is going to be running through the center here. So if it's 300 mil, to the top surface is going to be 150 mil. So this distance here, and actually to the bottom surface is also 150 mil. So y is 150 millimeters. So times by 150 times 10 to the minus 3 over I, which we've got in part A and part B. So 1.86 times 10 to the minus 4, which is 52.9 times 10 to the 6 newtons per meter squared, or 52.9 megapascals. And then part E then goes on to say, comment on where the maximum stress will be and if this is compressive or tensile. So that stress is in the middle of the beam, because M is our moment, is the maximum in the middle of the beam. We've calculated M in the center of the beam. Y is as far away as possible from the neutral axis, so either on the top surface or on the bottom surface. Okay, on the top surface it would be positive 150. So actually in this example we've assumed it's on the top surface. If it was on the bottom surface it would be negative 150. And an I we've got for this section. So my stress 52.9 megapascals. That's actually going to be on the top surface of the beam, and it's going to be compressive, and it's going to be in the center of that beam. If we calculated it on the bottom surface, we would have needed to put Y as minus 150, and we would have ended up with minus 52.9 megapascals. So that would have been the stress on the bottom surface, and actually that's the minimum stress, and that is the tensile stress equal and opposite to the stress on the top surface. So the stress on the top surface would be 52.9 megapascals. The stress on the bottom surface would be minus 52.9 megapascals in the middle of the beam. So compressive at the top, tensile at the bottom.